Hello physics students. Welcome to our second video in the electrostatics of distributed charge unit. And before we begin with today's information, I just want to summarize what we learned in the last video lesson. Remember, we tried to find the electric field for an arc of charge. If I take something like this and I spread the charge on this line evenly across it, and then I bend it into an arc like this, and then I try and find the electric field at the center of curvature of that arc. And I can't use kq over r squared for the entire arc because that only works for a tiny point of charge. So what I could do is I could use kq over r squared. I hope I said that the first time. I could use kq over r squared for a tiny little slice of this. If I make it small enough, it looks like a single proton or electron, depending positive or negative. And I could use kq over r squared for that portion right here. And I could figure out the length of that arrow from that formula kq over r squared. Then what I have to do is add up all the pieces. And of course, what I'm doing when I add up tiny, tiny little fragments of something, I'm integrating. And as I integrate it around, I realize that the only component that would survive is the horizontal part, because any vertical part would be later canceled by the vertical contribution from another part of the arc. So that was the process. We use kq over r squared for a tiny piece of the object, and then integrate after selecting the correct component that survives to get the whole electric field from all the pieces. So today we're going to use that same process for the next shape, okay? And that's what we're going to be doing throughout this topic, is we're going to be using kq over r squared for pieces and integrating for different shaped objects. Today's object, well, I've got my garage garbage can, okay? So here, the ring around here is a circle, right? So it's a ring. And then what I'm going to do is just rub along the ring with fur. And of course, that'll deposit charge evenly along this ring. And then I want to find the electric field caused by that ring of charge. Okay? But not in the middle where we found the electric field for just an arc, because in the middle it's zero. We have electric field, if this is positive, pointing this way, this way, this way, this way, it cancels. So in the middle, the electric field right at the center of this circle is zero, okay? We want to find it along the axis that goes through the center. Nowhere else, anywhere else like over here, too hard of a problem. Only along the axis, and it's going to be hard enough. Okay, so what I do is first, so let me step aside. So here's the problem. I'll pause and let you jot this down, then I'll explain what's here. Okay, so determine the electric field on the z-axis. And here's our ring. And I hope you like the way I wrote R. It looks like hopefully it's on the surface. You don't have to do that. I just like it because it's fun for me. So the first thing I'm going to do is I'm going to charge this up with a negative charge evenly around the ring. That means it has a linear charge density of charge per length, the length being the circumference of the ring, 2 pi r. So, again, I can't use kq over r squared unless I pick a tiny piece of the ring that looks like a point. That's what I've done here, a little dq right here. And since the ring is negative, it'll point directly at this, because it's like an electron here, right? Points directly at this point. And the charge there is the coulombs per meter, that's what lambda is, times the meters, the ds, the length of that little arc. And so, here's lambda, right, for what I calculated, charge over length, times the length of that arc. That's the charge right there, okay? So I can use kq over r squared to figure out the length of this dE. But before I do that, I just want to point out that we only want a particular component of this dE. if I bring my trash can back here, it'll help you see. So here's the axis, right? Let's suppose I'm considering a point over here and a point over here. These are both negative charges. So this point over here makes an electric field represented by this marker. So maybe this is an arrow, this green marker, pointing directly at this point. On the opposite end of the diameter, there's another negative here that makes an electric field pointing this way. So the purple marker. And what you should see is that these have the same horizontal component, these two dE vectors, electric field vectors. So those horizontal components cancel. It's only the vertical components that survive. So it's the Z component that I want to integrate. Okay? So I could state right away that the electric field in the X direction and in the Y direction equals 0, just from the geometry of the situation. And then what I want to do is I want to get the dE in the Z direction. What that'll be is it'll be this electric field arrow, dE, whatever length it is, times the cosine of this angle, because I have a little right triangle here. It doesn't quite look like a 90 degree because of the perspective, but this is a 90-degree angle right there. So I want this part, I multiply the hypotenuse by cos theta, that gives me the Z component in the downward direction. Okay? Now what I'm going to do is I'm going to expand that. Okay, so I will say the dE is, like in the last video, kq over r squared. So k, the q is all of this, the charge that's inside that little speck of the ring. So let me go ahead and fill that in, minus q Now, what's the radius? The radius is not the radius of the ring. The radius in kq over r squared is how far away the charge is from the point where the electric field is being studied. That's this, which is basically a hypotenuse. If I redraw this geometric triangle, like this is the radius. This is a 90-degree angle, and this is the Z coordinate above the center of the ring. This, by the Pythagorean theorem, this C squared is that squared plus that squared, so C is radical Z squared plus R squared. Okay? So, R squared is that squared. In other words, there's the electric field arrow length right there, dE. Now, the cosine theta, I could get rid of the theta variable because it's here, and therefore I could replace the whole function cosine by looking at this triangle, and the cosine of this angle is adjacent side over hypotenuse. There's the adjacent side, there's the hypotenuse. Adjacent over hypotenuse. Okay, so moving on. I'm just going to sort of touch this up and split up the, combine the brackets and get rid of the fraction within a fraction. And so I have this. Oops. That may not be visible on the camera. Let me make that a little bit bigger, to the 3/2 power. And then we have ds. Okay? So I put the 2 pi r down in the bottom, because that's where it belongs. I have in the top k, q, and z. And then these two combine to the 3/2 power. Okay? That is the z component. Oh, you know, maybe I have to pause here to give you an opportunity to catch up. So that is the z component of just this one little piece. But we don't want just the z component of one little piece. We want it for the entire ring, okay? All of the pieces added together. And so when we add little bits of something over and over, again, integration, the magic of integration. So we're going to integrate this. But let me make a little room. Okay. So now instead of dEz, we're going to have the whole entire Ez, the z component of the electric field. Maybe I need to bring it down a little bit. Integrating. Hold off on the limits. Leave a little space. Minus k, q, z, ds, 2 pi r, z squared plus r squared. Now, this may look like a very complicated integral, but as I'm integrating around this ring, right, maybe I shouldn't erase all of it. The z-coordinate's not changing. Well, k and q aren't. Q is the total charge. The z-coordinate's not changing as I'm going around this ring. All the points here are a certain z below that point. So that doesn't change. Neither does the radius of the ring. Z radius. So the only variable is ds, arc length. And so we're integrating the arc length around a circle. So the limits are from 0, your starting point, to the arc length when you've completed the whole integration around the entire ring. That's 2 pi r, the circumference of the ring. So a real easy integral. Because everything is a constant, as I said, it can just come out of the integral. And ds integrates to s, just like dx integrates to x. Well, ds to s. And the limit's 0 to 2 pi r. The only thing left, plug in the limits and solve. So let's do that. Okay, so plug in the limit once and then plug in the other, 0. And what you could see is the 2 pi r will cancel here and here. So that leaves us the EZ All right. Not too bad. At least I think it's not too bad. Hopefully you do too. Okay, so before I review what we did, I just want to remind you that, remember yesterday or in the last video, I said that very often you're going to start getting more and more complicated functions for the electric field. And what you should do, my recommendation, if there's time, of course there's an AP and there's no time, then don't do this. But if there's time, you got a minute or a few seconds, look at this formula to verify that it has the correct units. The basic formula for electric field is kq over r squared. That means we need a k constant with all the units that come with it. Q is in coulombs. R squared is in meters squared. So does this formula satisfy that? If it doesn't, then then it is wrong. So we've got a K in the top. We've got a coulomb. Okay, looking good. But here we've got a meter in the top. And then the bottom, we've got meters squared to the 3/2 power. If you do something squared to the 3/2 power, it's like taking the square root and then doing it to the 3rd power. That gives you meters cubed. And what you can see is that, yes, the units are correct, right? So this can go like that, and we got a squared up. Well, it's not a very good color to see, but there's a squared. So K coulombs over meters squared. So the formula looks like it is accurate. Of course, if we are missing a constant here, and the 2 should have been really belong there, this would not find that error, but it would find an error, like for example, if this was cubed down here, then we would catch that mistake and we'd go back and look and see and find out how come it should be to the 3/2. All right, so again, let's review the solution. Okay, and so what we did is we imagined with this ring, a little tiny, like an electron here, kq over r squared. We knew we had to pick the vertical component, the z-axis. That's why we said dE, this length arrow, times the cosine picks the z component. Then we filled this in with kq over r squared. Always you use kq over r squared. And then with the trig function, we were able to get rid of the cos theta from z, r, and then the square root of it. So that's cosine theta right there. Then we integrated the final expression here, and it was just ds to s. Nice, easy integral. And that's the electric field on a ring. But one last thing. Very often, they want you to sketch a graph of what the electric field looks like. This is a formula representation, but they want you also to create a graphical representation. Sometimes the patterns are clearer with a graph. So we're going to be creating lots of graphs this year. So let's make an axis for the electric field in the z direction. And then the z coordinate like this. And what you could see is that for positive z, well, first of all, for z equals 0, the electric field is 0, right? Put 0 there, you get 0. So we knew that already. We talked about that in the beginning. So it goes through the origin. And then for positive z, the electric field is negative because of this minus sign. That makes sense also because this ring is negative, so the electric field points toward it. So it's down electric field. So, and then this function, if you were to put on a TI calculator, would look something like this. It would peak somewhere here, and then gradually go to 0 as z goes to positive infinity. If you put in negative z here, negative, negative, you get a positive electric field. That makes sense also because if we have this ring below, down inside this trash can, the electric field will point towards towards the axis, which is in the upward direction, because this is negative. So that makes sense also from a physical standpoint. But basically, you've got a mirror image like this. So that's the electric field as a function of z. Sometimes you have to find these maximums by taking the derivative of this with respect to z, setting it equal to 0. That comes up later in example problems. So that's it for today. The electric field of a ring, you always use kq over r squared to find one vector, pick the component, and integrate to get the total. All right, I'll see you in the next physics video where we'll look at a different shaped object and charge spread across it.